Okay, here we have our final unit in AP Physics 2, Unit 7, Quantum, Atomic, and Nuclear Physics, just modern physics in general. And so there's only 4 equations you need to know here, but there's a lot of content, so we better start right away with our content review. Okay, a bit of review. What is an atom? An atom is just the smallest particle that has specific chemical properties. You have protons, electrons, and neutrons, but that's just review. We have new stuff now. There's something called a quark, which is just a fundamental particle that's indivisible. An electron is also a fundamental particle, but a quark makes up protons and neutrons. Protons and neutrons are not like electrons. They are heavier than electrons, and they are made up of fundamental particles themselves. And so a quark just makes up these, a set of 3 quarks always make up protons and neutrons. There's 6 different what's called flavors of quarks. I don't know why they call it that. It's kind of quirky. But the 2 most common ones are up and down quarks. And so up quarks have a charge of positive 2/3 E, where E is the fundamental charge of an electron. And down quarks have a charge of negative 1/3 E. And now I know what you're thinking. How can you have a fractional amount of the fundamental charge? Isn't the definition of the fundamental charge that it's not fractional? Everything has to be an integer multiple of that. Well, when you get into quantum physics, everything breaks down. Like classical mechanics just breaks down. So hang on for a minute. You can have charges that are fractions of elementary charges if you are a fundamental particle yourself. Some of the other fundamental particles, like I said, are electrons. We also have neutrinos and photons, which we're probably going to talk about a little bit in this video. Now, how do you make a proton? You're going to have 2 up quarks and 1 down quark. And so when you have 2 up quarks, that's 4/3 E, and then 1 down makes it negative 1/3. So 4/3 minus 1/3 is 1. And so that's a proton. Neutron, you want 0, and so you have 1 up quark and 2 down quarks to cancel it out. Okay, that's a bunch of new content, but going back to old content, nucleus is just the positively charged collection of protons and neutrons at the center of an atom. And we say a nucleon is just a proton or a neutron, just particles that make up the nucleus. And the reason why these nucleons stay together is because of what's called the strong force. Protons generally repel each other because they're like charges, but the strong force is stronger than that at a very short range, which is just in the nucleus of a atom, and it binds the quarks to form nucleons and also binds the nucleons to form the nucleus. Very important force right there. You can describe an atom in 2 ways, atomic number and mass number. Atomic number is just the number of protons it has, and mass number is the number of nucleons it has. And so you can say something like boron B has 11 as its mass number and 5 as its atomic number. So it's 11 nucleons and 5 protons, meaning 11 minus 5 is 6. It has 6 neutrons. There are variations of atoms as well, ions and isotopes. An ion is an element with a different number of electrons, and so it can be positively charged or negatively charged. We actually talked about this very briefly in Unit 5 when we had an FRQ problem that mentioned cations and anions. Those are the 2 different types of ions, either positively charged or negatively charged. And then there's also isotopes, which are elements with different number of neutrons. And so, for example, there's 5B, boron with 3 neutrons and 5 protons, and also 5B. And so that's 8 neutrons and 5 protons. And some of these are unstable or radioactive. Speaking of radioactive, there's 4 different types of radioactive emissions. Those are just decaying of unstable atoms. There's alpha decay, which is when a combination of 2 protons and 2 neutrons just leaves. There's beta plus decay and beta minus decay. Beta plus is when a proton changes to a neutron and that it releases something that we cannot talk about yet. Beta minus decay is when a neutron changes to a proton. And then finally, there's gamma decay, which is just the emission of a high energy photon. Photon is just carriers of light, and so it's just very high energy. It's called a gamma ray that is just emitted. You might actually remember gamma rays from our last video in the electromagnetic spectrum. It's the lowest. It has the shortest wavelength, which means it has the highest energy. And so that's why gamma rays form high energy photons. And energy emission of atoms. So unlike popular belief, energy emission is actually discrete and countable, not continuous. This is what we used to think. We thought it was continuous. It's actually discrete. And the reason why this is true is because electrons jump between energy levels. So if you have an atom like this, an electron can jump from one energy level to another, and an emission causes jumping down a level, while an absorption causes jumping up a level. And so you have what's called a spectra, and these various lines on the spectra are absorption or emission lines, so that when that specific wavelength light is emitted, then an electron jumps down a certain wavelength, to a certain energy level. And these are discrete because you cannot have a light hitting at some point and in the middle of these energy lines, and the electron jumping down to another energy level, because it has to be at one of these discrete points. We'll talk a bit more about that later, but this is just evidence of what's called the particle nature of light. We talked about waves nature of light in the previous video. That's all waves and stuff. This is particle nature mostly. So a bit more about radioactive decay. A nuclear reaction is just a chemical reaction that involves a nucleus, and there's two types: fission and fusion. You might know this before just from reading the news or whatever. Fission is when a nucleus splits into two smaller parts, and you can induce this by colliding nucleuses. So you have two different nucleuses of different atoms, and you just combine them together, and you can cause fission. Or you can add an additional neutron to an atom, and that just causes fission because it becomes unstable, and alpha decay, for example, occurs. Fusion is where multiple nuclei combine into a large nucleus. So, for example, the most common type is hydrogen fusion. Two hydrogens combine into a helium, for example. And every time during a nuclear reaction, there's conservation of mass, charge, and momentum. Mass means the total number of nucleons is constant. Charge means that the total electric charge is constant. And momentum just says that the momentum of the atom and the emitted particle is constant. And while the kinetic energy does increase because it's a scalar quantity, the momentum is vector quantity, and so they point in opposite directions, and therefore they cancel out. So if you have fission, for example, of two atoms just splitting apart, they have momenta that point in opposite directions and cancel out to form the zero that it was before it split apart. You've probably heard of this before. E equals mc squared. I'd be very surprised if you have never heard of that. That is probably the most famous equation other than F equals ma. And this is Einstein's famous equation. It basically says that you can interchange mass and energy in some scenarios. A very tiny amount of mass is lost during nuclear reactions. We did say mass is conserved, but we're going to talk a bit more about that in the future. We're going to refine that a little. A little bit of mass is lost, and to compensate for that, a lot of energy is gained. For example, if you have like 0.000001 grams of energy lost, this is c squared. C is the speed of light. That's 3 times 10 to the power of 8. Squaring that is 9 times 10 to the power of 16. That is a lot to multiply by. It's like dollar conversions, right? You give $1, you get €1, for example. That's a very small conversion rate. You're just multiplying by like 1 point something to get from between euros and US dollars. But this is 9 times 10 to the power of 16. That is a lot. And so even if you have a very, very minuscule amount of mass, you're going to have a lot of energy that's produced. And that's the entire point of fission and fusion. If you have an atom that's smaller than iron, it's actually fusion that releases energy. But if you have something that's larger than iron, fission or decay just releases energy. If you have iron itself, you cannot gain energy from that. And one important consequence of this is in stars. When you have really massive stars, they can keep on doing fusion. It's usually just hydrogen to helium, but as they start to die, it becomes helium to so on. Helium to like lithium, or helium to beryllium, and so on. Carbon, oxygen, iron. You finally get to iron, and you're not going to get any energy from undergoing fusion with iron, because if it's smaller than iron, fusion releases energy, which is what a star is trying to do. But once you get to iron, you can do fusion, you're not going to get any energy. And so that's where it stops. You get an iron core at the heart of a dying star. Okay, brief interlude over. Back to E equals mc squared. This is called the rest energy, or the energy due to a mass. And so two new units we're going to talk about is a mega electron volt. 1 mega electron volt is just equal to 1.602 times 10 to the power of negative 13 joules. It says mega in it, but it's still a very small amount of energy. Then there's 1 U, or AMU, which is atomic mass unit. And that's 1.6606 times 10 to the power of negative 27 kilograms. these two are very useful when we're discussing small amounts of energy and small amounts of mass that are involved in nuclear reactions. There's another type of energy of a photon, or energy due to light. That's just E is equal to hf, where h is Planck's constant. H is equal to 6.626 times 10 to the power of negative 34 joules per hertz. And so when you multiply by C, Hc is equal to 1240 electron volts times nanometers. Oops, not times meters, times nanometers. And so another form of this is equal to Hc over lambda. And this is probably more common because Hc is just 1240. It's very easy to memorize. Over lambda, lambda you can have in nanometers, and you'll get a good answer. And so the energy of a photon just represents the discrete values of an energy that an electron can emit or absorb, just like we talked about before. Okay, conservation laws, back to these three. Instead of mass, though, we're going to be talking about what's called mass energy conservation. Conservation of mass is just mass cannot be created or destroyed. Conservation of energy is energy cannot be created or destroyed, but it can change forms. And conservation of mass energy is what we're talking about now, which is a difference in mass is accompanied by an equivalent amount of energy based on the rest energy. And so these other mass and energy conservation laws do not hold during a nuclear reaction. It's only mass energy that holds true. And so when you lose a bit of mass, you get energy that is released. So that's mostly about the particle nature of light. We're going to revisit that later. But now what about the wave nature of particles? All particles have wave-like properties, specifically a wavelength. It's called the de Broglie wavelength. The pronunciation is weird. You say de Broglie, whatever. It's DBROGLI. That's the wavelength. And that's just the wavelength of a certain particle. Electrons have wavelengths, for example. And the formula for this is lambda is equal to h over p, where p is the momentum. So the more momentum you have, the smaller your wavelength is. So it's also h over mv, because momentum is mv. You should know that from AP Physics 1, which means it's also hc over pc. You can cancel off the c's here, but actually hc is useful because it's just 1240 electron volts times nanometers. And this means that if they have wavelengths, particles can also be diffracted. So you just use the formulas we learned from the previous video about the m lambda, d sine theta, things like that. That's all about diffraction. You can do that with electrons and particles as well. There are also particle-like properties of waves. And so that's kind of what we talked about earlier with photons. Photons is just a quantized particle of light. And so the energy formula for that is this. And the intensity of light is just the brightness of light, and it's proportional to the number of photons emitted. And that is just pretty important. And you can also use these wavelength formulas to say that the momentum of light, or of a photon, is equal to h over lambda. You're just rearranging the de Broglie wavelength formula to get the momentum of light. You're using it for a different purpose. There's a few more things that really do not belong in this section, but it's relativity and Doppler effect. Relativity basically is all measurements are relative to an observer, so there's no absolute measurement. So for example, if two observers are moving with relative to each other, so one is on a train, one's just standing still, if their relative motion is slower than 10 to the power of 7 meters per second. That means that they only disagree on the speed of objects. So, for example, someone on the train drops a ball. They see it, or for example, throws a ball. They see it moving with some velocity, but the person standing outside the train sees the ball moving at a velocity that's added to the velocity of the train, because the train's moving too and the ball's moving inside of it. And so they disagree on the speed of the object. But if the relative motion is greater than 10 to the power of 7 meters per second, then they disagree on the speed of objects, they disagree on duration, and they disagree on length even. But they always agree on the speed of light. That's always going to be constant, no matter what. And so, yeah, if you have more than 10 to the power of 7, that's what we usually consider relativity. That's when there's length dilation and time dilation and things like that. Another thing, I said there's no absolute measurement. That means that there's no privileged frame of reference. There's no one frame of reference that's true no matter what. All of them are true, just from different points of views. It's like that common story about someone writing a 6 on the ground, and then one person looks at it and says, oh, it's 6. And another person looks at it and says, oh, it's 9, because they're looking at it backwards. And so both of them are right from their own point of view. You don't know which way you're looking at. you could be looking at a different way from the other observer, and so that's why you disagree, but you're both right in the end. One thing to note is we're not going to get into any equations with dilation and things like that, but motion through space does decrease motion through time. So if you increase your speed through space, you're going to slow down time, basically. And then the second thing is Doppler effect. Doppler effect is just going to be where you have a light source or a source of a wave that's moving with respect to you, an observer, and it has a certain frequency f. If the light source or a wave source is moving towards you, then the frequency is going to increase. Because think of it this way. You have something emitting a sound. Just normally it emits something like that. But if it's moving towards you, it kind of moves like this, where this region is closer together than this region. And so the frequency here is greater because it's closer together. And so if you're moving towards the observer, the frequency is larger. If you're moving away, the frequency is smaller. And that's what redshifting and things in astronomy are about. Okay. After that, we're going to get back into the particle nature of light with something called the photoelectric effect. Fun fact, this is actually what Einstein won his Nobel Prize for, not for relativity or anything like that, or even E equals mc squared. Even he won it for the proving the photoelectric effect, because back then, and I think even now, the Nobel Prize is only given for like experiments, not theories, because you cannot really prove a theory that well. If you do prove it, then yes, you do get the Nobel Prize. But if you cannot prove it, you just theorize something. And even if most people believe it, you cannot get the Nobel Prize for that. Okay, back to this. The photoelectric effect just says that when you shine light on a metal, there's electrons going to be emitted. One important thing related to this is called the work function, phi. That just says that's just the amount of energy required to remove an electron from the surface of a metal. So it's not really a function that it kind of does take in an input. The input is like the metal, and the output is the amount of energy required to remove electrons from that surface. Another thing is stopping potential, Vs. V is the potential, and stopping potential is just the electric potential that's required to stop a group of electrons. So a group of electrons are moving, you just stop it, a potential is required for that. And the equation here is K max, the maximum kinetic energy of a group of particles, is going to be equal to 1/2 mv max squared. That is obvious. That's just the formula for kinetic energy, which we know from AP Physics 1. But what's interesting is this is also equal to Q times Vs. This is also a type of energy, it's just electric potential energy. But this says that the maximum kinetic energy is equal to the electric potential energy required to stop it, which does make sense, conservation of energy. Another formula, one on the equation sheet, is HF minus phi is equal to K max. All of these are types of energy. This is the energy required to remove electrons. This is the energy of a photon itself. And this is the maximum kinetic energy of a group of electrons that are being emitted. So what this is saying is that the kinetic energy maximum of a group of photons or electrons that are emitted from a surface is equal to the amount of energy of the photon that struck the surface of the metal minus the work function. So basically it's saying that out of all the energy of the photons, some amount of it is being dedicated to the work function to actually dislodge an electron, and the rest of it is the kinetic energy of the electron that is dislodged. Why is this important? This is based on the conservation of energy. Like I just said, all of this is conservation of energy because all of these are types of energy, and it's basically saying that if you add up the work function, the amount of energy to dislodge an electron, plus the resulting kinetic energy of the electrons, you get what the energy that started off with. Now, a few counterintuitive things. If you increase the frequency of the light, that only causes the electron kinetic energy to increase. This increasing this frequency only changes this. It does not change the frequency of the electrons being emitted. It doesn't mean that more electrons are going to be emitted. It just means that each electron has a higher kinetic energy. On the other hand, if you change the intensity of the light being struck on a surface, that causes a higher electron frequency only. It does not change the electron kinetic energy. Yeah, try to remember that. Definitely important. And the reason why this is important, the reason why Einstein won a Nobel Prize for this, is because it can only be explained using the particle nature of light. And so this is basically proof that light exists as a particle as well. Last section about wave functions and probability. So when you have radioactive decay, there's something called a half-life, which is just the time for half of a given radioactive material to decay. And so if you have certain amount, after a certain half-life has passed, let's say the half-life is 5,000 years. After 5,000 years, approximately half of the sample will be left. And then 10,000 years from the start, only 25%. And then if you continue on like that, it's just going to keep on decaying until it's just very small. Now, this can only predict the behavior of a large number of nuclei. It's not like saying, oh, there's one nucleus only. That means that it's going to decay after the half-life. No, a single nuclei only has a 50% chance of decaying within the half-life, because after all, it is a half-life, so 50%. That has to do with probability, but another thing with probability is the wave equation or wave function, phi, or this equation. It's a Greek letter. You probably don't know what it's called, but it's just the wave equation. The probability density function of position. So basically, this is kind of the density of the probability of finding an electron somewhere. And this squared of r returns the probability of finding actually an electron at a certain distance r from the nucleus. And so that's pretty important in quantum physics because that has to do with like probabilities and things like that. Final thing, electrons as waves. We talked about that a little bit with the de Broglie wavelength. That just explains the energy levels of electrons because the wavelength is going to be the de Broglie wavelength is if you have the integer multiples of that, that's going to be the circumference of the energy level. So you have these energy levels around the atom. The circumference of that is going to be an integer multiple of the de Broglie wavelength of the electron. And that's it for the content review. Our first question here is going to be about the Doppler effect. It says that there's a laser beam every 5 seconds. So the frequency should be 1 over 5, which is 0.2 hertz. But the ship is approaching the planet at a high speed. And so that means it's approaching the planet, so the frequency should increase. It's an observer situated on the planet. And so the frequency should be greater than 0.2 hertz, since frequency increases when the source is moving towards the observer. Okay, second problem here. Specific radioactive material is found to decay such that 25% of the original sample remains after 100 years. What is the half-life of the material? This is pretty simple. If it's 25%, we know that first it's 100, then it's 50 because half-life, and then half of 50 is 25. So this is 2 cycles later. If that's a total of 100 years, that means each cycle should be 50 years. So our answer would be C. And this FRQ practice looks very long, and it is pretty long. But most of it is just a big graph that's taking up a bunch of space. So let's see. An experiment is carried out, different colored LED lights, and which are connected one at a time to a variable voltage supply. When the voltage supply is set to 0 volts, none of the LED bulbs are lit. As the voltage is increased, each LED light turns on at a different voltage setting. As the voltage is further increased, the brightness of the LED increases. And so the data is collected of the color wavelength and corresponding frequency for each LED and the smallest value of the voltage where the light is illuminated. So this is the data table right here. It says for the different colors, it has the wavelength and frequency of the light as well as the voltage it takes to light it. For part A, explain why an increase of delta V equals 0.1 volts in the voltage after the light is illuminated causes the brightness to increase, but the bulb remains dark for any of the LEDs with the same voltage increase from 0.1 volts to increase delta V equals 0.1 volts from 0 volts to 0.1 volts. Okay, so this has to do with the photoelectric effect. The work function is just the amount of energy which must be supplied before a photoelectron or just an electron is released. And so there's a certain amount of energy that must be added before an electron is even dislodged at first. And so for any amount of energy supplied by this variable voltage supply that's below the work function, that means there's going to be no electrons emitted. And so the work function of the material must be greater than 0.1 electron volts. So work function has to be greater than 0.1 electron volts since there were no electrons emitted when the voltage was 0.1 volts. Okay, part B, it says, explain that's plot the data on the axes below. Then calculate the slope and y-intercept of the plot. And so what we can do here is just show like the different plot points on here. It has frequency versus voltage, and so frequency is 4.62. That's going to be approximately here, and the voltage is 0.51, so around here. Then 5.17, 0.74, 5.17, 0.74, that would be right there. Okay, 5.64 and 0.93 is around there. I'm just doing it approximately, by the way. 750, that's here, and 1.71, that should be right around there. And so we actually do see a pretty nice line. We could draw the line of best fit around here. And if you were to actually extend the graph below the x-axis, you would see something pretty interesting. I'm actually going to do dotted lines for this so we can see it. But the slope, you can calculate by doing a slope triangle. You just pick 2 points that are not data points. They cannot be data points because the data points are experimental. If you actually draw the best fit line and then use 2 different points on the line to create a slope triangle, that would be more accurate. And so you can calculate that. You're going to get B, the slope m is equal to 4 times 10 to the power of negative 15. And the unit for this is going to be volts times seconds. And you can figure that out because it's just volts divided by hertz. That's the unit for slope. And hertz is 1/seconds. So volts times seconds. And the reason why this is true, you do 2 different points and just do delta y over delta x. The y-intercept, you can extend it down. You're going to get B, or the y-intercept, is equal to negative 1.4 volts. You notice something interesting here. The slope is actually the value of Planck's constant. The reason why is because the energy is equal to HF. And so energy is just voltage times... and so this represents the amount of voltage you need to add, and H is Planck's constant, F is the frequency. So that's a nice equation we can use. But there's also minus phi. This is basically what the entire equation is. That's just K max, but we can also use energy because that's the energy of the electrons being emitted. And so the y-intercept is going to be the work function because when the frequency is 0, the entire energy is just going to be the work function. It's not going to be at that point because you're not going to have an energy. You cannot have negative energy. But if you extend it backwards, you're going to get the work function as being the y-intercept. And part C, explain how, if possible, this experiment could be repeated to get a plot with the same slope but different y-intercept. If this is not possible, explain why. So you're going to need a different work function because the work function is just the y-intercept. So you need LEDs that are a different material, and that would change the work function since the work function depends on the material. So for C part 1, you just change LEDs. And that gives you a different material, which is a different work function. Part 2 is you want a different slope but the same y-intercept. This is actually not possible. The reason why is because the slope is Planck's constant, and Planck's constant is, as the name suggests, a constant. You cannot change that. And so that would be our answer for the FRQ. Well, we have come to our end of the AP Physics 2 journey. This is our last video, and we, just good luck on the AP Physics 2 exam. Hopefully all these videos prepared you well. And yeah, good luck on that test.